Welcome aboard then, if there isn't any questions about the 4.3 things yet. Slopes, tangent lines at a general point. Last time we did them at a number, like a 3 comma something, -5 comma something. But before we go, like I said, we're doing things for money, another sponsorship thing. I'd like to put in a little ad for Campbell's Soups, the taste of home. Campbell's Soup. Curl up with a good bowl of soup, do some math, and soup, guys. Cream of mushroom soup. It's good stuff. There's a typo on this one. Anyways, who would have thunk? Campbell's Soup. It's brought to you by Campbell's Soup. Welcome to Calculus in the AM. I'm your host, Mr. Sudelka, and we are finding the slopes of tangent lines about the general point. So this time we won't use like an actual number. We're going to say x, and we know x represents, it's a variable. So finding the derivative is actually what we're doing. So what is finding the derivative? Derivative is the slope of a tangent to a point on a curve. So we get this idea here, this tangent line to a point P right here, right? The slope of the tangent line, if you can calculate that, that's the finding the derivative. It isn't actually drawing the tangent line. It's connected to it. But that's what we're talking about when we say this. So we've got a little rundown here. And let me just flip a root. But I think we know what the slope of a line is. Slope of PQ. Now here's the idea, right? The slope between here and here. So I'm going to grab this off. Right? The slope of the line PQ is, well, we usually put y2 minus y1, right? So we'll start with this. Even though we know this. I'm trying not to skip too many steps. Now, in this particular case, I'm going to keep thinking back to what we were doing before. Remember how the other day, if we said that this point P was at 2, right? We would have said the second point that we're pulling in is like at 2 plus h, where h is this little infinitesimal thing so close to 0, we'll almost think of it as 0. But we need it, h, because we can't divide by 0. And we said, well, of course, 2, if this was 2, would match with f of 2, whatever the function gives you at 2. So here we got x matched with f of x when those disappear, right? Likewise, that x plus h value, how'd you find the corresponding y value? Well, you plug it into the function, f of x plus h. And that's where the work comes in. So our next thing in notation is to say y2 minus y1. We're not going to put y2, we're going to put f of x plus h. Whatever you get when you plug that into the function. Who knows what the function is? Could be x squared. Could be x to the 5th minus root x minus 2x to the -1 or something. Subtract the other y value, f of x. So just with the function. Now, x plus h is the first term, or the first term to plug in, x2, minus x. Now keep in mind that we have to, well, that music is just distracting me, and I forgot what I was going to keep in mind. Sounds really mysterious, doesn't it? You solve a mystery or something like that. Sort of Sherlock Holmesy or something. Anyways, I'll just f of x plus h minus f of x. We can't simplify that right now without an actual function. The bottom, though, comes out to be x minus x, right? X plus h minus x. So just h. Now this is where we get to this idea make it big, that this h, we haven't put the limit down there, but we're bringing it closer and closer here. We're making this h distance right here, smaller and smaller all the time, getting it down to 0. What's the problem with that? You can't divide by 0. So we can't just do this with arithmetic, we have to use calculus. And that's this limiting idea, right? And you might find it unsettling at first because with the other examples, we had actual numbers. We had 3, comma, -2, and so on. Here, we're not going to have that. We're going to have just an x expression on the top for f of x, and well, x minus x. That eliminates. We're going to have just h on the bottom. But we want to make this h as small as possible, so we need to use a limit, what we say. So this is what we're going to have here. So the slope is equal to limit h approaching 0.
Will it always be approaching 0?
Yeah, it will. If we're finding the derivative, it will. So, this essentially is the definition of the derivative. You need a lot more explanation of this, but it's always, like Ava was clarifying, h approaching 0, meaning this distance here and here has to be coming together. It has to be getting smaller. That's the h, the distance between x and x plus h, right? Otherwise, you're taking the slope of a secant line, 2 points, actual points that lie on there. Here, you're taking the slope of where it hits at 1 point. Now, the definition of the derivative, like I said, it's essentially what I have written up there, but we're going to need a few words to just come up with here. I'll use blue. If y is a function of x, so y equals function of x. That just means like x squared minus 3x, isn't it? Then the slope of the tangent line to the curve f of x whatever that describes, like x squared minus 3x or something. At the point x comma f of x. Is given by, now here's a notation thing. F prime of x, which equals that thing we just wrote down, that limit h approaching 0, f of x, separated by that small distance h, which comes to 0. Subtract f of x. All divided by h. You can't evaluate that without a limit, without calculus.
So this is kind of like a general equation.
So this is kind of a general equation. Yes. In a sense, this is what I was going to say with the description here, right? This is all formal and stuffy. I wasn't too careful about my sentence, but it's somewhat. To describe what the derivative, what are you finding when you're finding the derivative, or what is the derivative? It's kind of the slope, and what were you thinking? Where that h approaches 0, yeah. So you're taking the slope where this distance here is basically you've overlapped. But you can't take a slope of point P to point P, right? Because you get a 0. So it's this idea that you're moving it in here, but it'll give you the slope of this tangent line. And really, what is the derivative? It's just a formula. And that's what we're going to write down. The derivative is a formula. And this is just a descriptive thing. formal definition. Derivative is a formula that gives the slope of the tangent line. To a point on a function. Now, it'll make more sense as we do a few examples here. Might not make sense. Let's just try this. Use the definition of the derivative to find the slope of the tangent line to this function. We've got it simple. F of x equals x squared at 2 comma f of 2. But we're going to do the definition of the derivative. The other day, we would have plugged in 2 right away, right? Into this and found that it's 4 and so on, right? And then went with 2 plus h and worked that out. Here we're going to do it just a little differently, right? So, well, we'll see. So, we're going to use the definition. So I'm going to write down, first of all, notation here. F prime of x. That, I didn't talk about this yet. This means the derivative. And it's just one way. There's other ways to show you the derivative, and I'll show you those as a dy by dx way too. So just think of it as the function with that tick mark there, meaning the derivative. And what is it? You're finding the slope thing. So the limit of, you got to kind of memorize that, but I hope you realize the rest of it is the slope formula simplified a little bit. F of x plus h. I'll write it out totally this time. All over h. Now the h, we know it's going to happen there. It's going to slide into 0. We have to put this in here, into this x squared formula. So find the, using the general formula, limit of h approaching 0. So here's how it's different than the other day. We actually put in 2 plus h. Here we're putting in x plus h into the square. So what I'm saying here is I'm evaluating f of x plus h into the formula, right? So x plus h, square it.
Why is it squared?
I'm sorry, what's that?
Well, are you putting 2?
That's what I was saying. This is where it's different than the other day. We would have specifically put in 2 plus h and so on. We're going to do the general, the definition of the derivative. So that means we're using x, and then we'll put the 2 in at the end. And I'll show you why. This is, it seems like more work. It's about the same amount of work, actually. But it's a shortcut. It's a time saver if you have to do many evaluations. And I'll talk about that at the end. So minus f of x, that's just the function, x squared here. All over h, h. Can't do anything yet. Now, we work out x plus h all squared. Keep it in mind, you know you're going to get 3 terms. Only losers from pre-calc 20 would square that out and have x squared plus h squared and nothing else, right? They're not losers, and they don't make that mistake. X squared plus x plus h, so 2xh, plus h squared. Subtract x squared all over h. Now, this part's the front square. I want to keep in mind, this wasn't the case here, but if this was a longer thing, like minus 3x plus 5, keep in mind, you have to drag that negative sign through if that's the case, right? That's a common error. And you'll know, you'll probably catch that you made that mistake because this next step anything without an h should eliminate. And you probably see that here. Look at this, positive x squared minus x squared. If you had other stuff behind it, if you forgot to distribute a negative sign, things wouldn't happen the way it should. Often you catch those things. So, I'm going to just simplify. I'm going to show a lot of work here. I wouldn't be surprised if you skip a couple steps. So that's what that cleans up to. Mathematically, can you see what happens with the h? You can distribute the division. 2x h divided by h plus h squared divided by h. You can only do that because you distribute it to each item, right? You can't just do one and then it's gone, right? That's another thing. Well, you guys start forgetting that for every 10 mistakes like that, not each time, I will shoot a dolphin. So, actually, I would never do that. Price you pay to get into SeaWorld, you can stay there. I'm not going to get thrown out. Anyways, 2x.
Now you go to 2? And
Almost, almost. Right now, we're evaluating the limit. We're getting there. So this is just about there. You can see though. H approaching 0, we could do this 2x, right? And Hashim is thinking, oh guys, you could have done this in one step once you learned the shortcut. It's sort of like, you guys remember completing the square to solve equations, quadratic equations? You don't? You do? Completing the square. It took a long time. Then you're told 2 days later after doing problems, hey, there's a quadratic equation, right? Sort of like this. You still have to understand the process, and I will ask you to use this formula explicitly on at least one question. So you can almost guarantee in university you will be asked. So what is this? Now, the left-hand side, I didn't write it each time down here, but it's f prime of x. This is the derivative formula. I'm getting to A's question here. We're not done the question. But I just wanted to rewrite it here just to really drive this home. We're not done. But what have we found? We found the derivative. And what is the derivative? The derivative is a formula that gives you the slope of the tangent line at any point on this curve. We're worried about the point where x is equal to 2, right? So this is where we put in our 2. So the slope of the tangent line at 2 will be found if I evaluate f prime of 2. It just happens to be 2 times 2. The arithmetic in part is 4. I'm using that. Now, if you look at this, what we did there, and I didn't take any shortcuts with my steps. I showed every step. I wrote out the definition. You'd probably skip into this. I would hope actually you'd write this out in full. But then maybe you would, I don't know, skip down to here or something like this. Some of you would do this step, and that's just great too. You'd probably actually maybe get to here and then skip to here, because you can see that, right? It's about the same amount of work as the other method. However, here's the advantage. If I had then part B, evaluate f prime of 5, or what is the slope of the tangent line at negative x equals negative 2? So we'll just throw this as an aside. What is the slope of, for this function, the tangent line at negative, I'm going to go with one even better, at negative 12, comma, f of negative 12. Okay, I got that, oh, goodness gracious. Is that joking? Negative 12, f of negative 12. Okay. Would you want to go through that whole process again now to evaluate at negative 12? No. In the yesterday's Friday's method, that's what you'd have to do. Now we have a formula that gives you the slope of the tangent line at any point in this function. And here it is, f of negative 12. I just apply this, 2 times negative 12. I think you do that in your head. The slope there is negative 24. What are we finding here? Now, just keep in mind what this is, x squared, right? Now, I'm not going to plot points. But at 2, we'll say this is 2 here. The slope is 4. Obviously, my scale, it looks like it's a slope of 1, but I mean, that's where it is, right? At negative 12, negative, it's going downward. The slope of the tangent line is negative 24. It's really steep. It's practically went straight up and down, right? That's what this is telling.
Is there a set tangent line?
I'm sorry. Yes, you could, any point you choose, and in between, like, doesn't have to stick to integers or rational. You can use rational numbers, irrational numbers, root 2. Every point, like you can imagine this is just everywhere you want, you could draw a tangent. If for some reason you're worried about, maybe for a physics problem or a marketing problem, you're worried about the actual rate of change, slope, at a particular point on a function, you'd use that. Now, we'll get into applications later, though, but right now, from your textbook this time, 1 AC, 4 and 5. Try those out. So, and I'm giving you not a lot of time, but enough time. Oh no, that's right, today